part of the lecture. I say again, so it's recorded. We are missing the first part of the lecture, it is essentially descriptive. And therefore, I mean, they constructed breakwaters or groins, and we see what these structures are. So again, beaches are extremely important, and they are the result of accumulation of sediments. Okay, this is a first classification, but there is also a genetic criteria, and a genetic criteria, for instance, divides the coastlines between emergent and submergent coasts. An emergent coast is a coastline that results from an increase of elevation of land, for instance, for tectonic activities. And usually these coasts are characterized by a slope of the land close to the coastline that is not really weak. Usually they are characterized by a significant slope. Submergent coasts are those who have been inundated by sea. And there is already subsidence, which is extremely important, and there is already sea level rise. Keep in mind that after the last glaciation, there was a sea level rise of 7 meters, 7. Okay? And there are, in my webpage, there is an example of a submerged coast. For instance, this is a picture of a beach, and you see here the beach is you see the sand just in the lower part of the picture, is protected by the structure that you see there. This is called a groin. A groin is a protection that is perpendicular to the coastline. The breakwater is parallel to the coastline. So the groin has the function of limiting erosion, because the groin basically induces deposition, because the groin stops the waves that are traveling with a component of the velocity that is parallel to the coastline. They stop them, they stop the parallel component of velocity, and therefore the suspended material falls down and there is sedimentation. So what you expect is at the base of the groin, so the end of the groin, the connection of the groin to the coastline, you expect to see some sand in the part that is exposed to the waves. And indeed you see some sand there. The picture is not really clear, but you will see other examples. The picture I was referred to is, this is an important bay in the United States. It's called the Chesapeake Bay, and it's extremely important from an environmental point of view. It is an example of submerged coast. The part of, that you see covered by the sea was submerged after sea level rise, after the second glaciation. And here there is, I think there is a video, because this is an area that is extremely important from an environmental point of view. And I think there is a video here that explains to you how they are restoring this area. And there is no audio now, we are not going to see the video. I suggest you, these are short videos, and I suggest you to have a look, because looking at a video, I think it's important to improve our English, but also to have a flavor of what they do in other countries. And this is a general suggestion that I give to you. YouTube contains a lot of educational material, a lot of interesting material. So another form of interactive activity that I would like to propose to you is try to have a look on YouTube if you find something that you deem it's useful. And if you find it, just at the next lectures, raise your hand, give me the link, and we can have a look together. I turn on the audio, we can do that, and it's a way to interact, also this one. And it's a way to discover what YouTube has to offer to you. Another suggestion, besides YouTube, try to do this experiment. You open a web page and you search in Google for Wikimedia Commons. All of the pictures, not all, but most of the pictures that I have in my website are derived from Wikimedia Commons. These are public domain information. So you look at Wikimedia Commons, and if you search here like beach, beach is not well defined, so you find too much information. And but there are several pictures that you find here of beaches, and you know, you can really learn about something. And you see here, for instance, you see what it seems are growing there. And you see that the beach has these shapes. There must be a reason for that. So if you see the beach that is not straight, but has this kind of shape, there must be a reason. And it will be interesting if you go there, not here, but if you go to our beaches here, and you see some strange shapes, try to understand why. Okay? Where there is these shapes means that here you have increased the position. Why this? Here you have increased erosion. Why is this? Usually this is the result of the presence of groins, and you see that you have a lot of pictures where you can understand. This is a cliff coast. If you just browse and you see what is a beach about. But what I suggest to you, for instance, we will speak about a dune in a minute. What is a dune? So you may go to Wikimedia Commons and see beach dune. This is the dune. We will see what is a dune, but what's important to know for you and for now is that the dune has vegetation typically. And it's extremely important for a beach, we will see that. Because the dune is the end of the beach, where seawater gets there, you don't have vegetation. But you have a line at a certain point that where seawater is never there. Even during high storms, etc., during storms, you have a line which is the extreme extension of the sea. Beyond that line, you have the dune. And why the dune is elevated? Why is that? Because at the extreme point where the sea gets, you have the position. Of course, because you have a storm arriving there, a very violent wave with a lot of sediments, a lot of sand, and where the wave gets there, all the sediment is released. And therefore you have an elevation of the beach. And the fact that the beach gets elevated builds a storage for fresh water. And there you have vegetation. And this dune is a protection for the beach, because it's more coherent, there is vegetation, it's more robust. And so you understand what is a dune. Look, this is a dune, you have vegetation. It means that here, okay, you may have, in this place here, you may have some water coming in occasionally, because you see water is coming in here, but evidently here you never have, at least for the age of this vegetation, you never had seawater arriving here. And this is why you get some vegetation. But inside here you got some water, because the water came in through this small channel. It's important to understand. This is the basis. So let's see if there is something else. I don't think so. Okay, here. This is the dune, and then you go, this is the dune, you see the difference between the beach with sand and no vegetation, and it's amazing, there is a line beyond which you have vegetation. Here it's not very meaningful. This is the kind of vegetation that you have over the dune. It's a vegetation that is resistant to spray, to salt spray, because of course they get some, you know, some dust, some spray, which is salted. It's a very weak ecological environment. you see that Wikimedia Commons allows you to see a lot of things. And it gets in your mind more than reading. So try to use also this method for memorizing. Okay, so classification of beaches, and it helps you to understand how they work. So try to understand whether the sea is eroding, whether it's not eroding, where it is eroding, why it is eroding. Try to understand what is the dominant direction of waves. If you look at the shape of a beach, you can understand also that. And it's not difficult. And this is the way in which you build your experience. Experience is not directly related to age. Experience is related to your capability to observe. Okay, this is the picture of the cheese. I forgot it was also in the PowerPoint. So, this slide basically means that beaches are very important from an economic point of view. There are several reasons, and I think that there is no reason for you can read them. And they are important for tourism, for seaborne trade, they are important because agriculture close to beach may be facilitated for some reason. They may be important for fishery, etc. So there is no doubt that we need to take care about them. And I already mentioned this, there is a lot of ecology, there is a lot of life, there is a lot of vegetables growing there. Now, let me focus a bit more. We will have a lecture dedicated to saltwater intrusion, because saltwater intrusion is a real danger. It's a real threat to beaches. But let me introduce you how it works. Basically, where you have a beach, you have permeable soil, typically. Permeable because it's alluvial material, so it's characterized by porosity. And if you have a cliff coast, probably you may have limited permeability. Where you have a mid slope, where you have a beach, there is permeability. Permeability which is driven by the porosity of the material. And permeability means that seawater intrudes into the land, of course. And you know, it's not bounded seawater by the sea bottom. The sea bottom is up there, it's here. This is the sea floor or sea bottom. But it's not a boundary for the salt water. The salt water intrudes. How much does it intrude? Of course, intrusion of salt water is regulated by permeability. If you have high permeability and you don't have fresh water coming from the land, which is never the case, you always have from the land some fresh water flowing into the sea. But ideally, if you didn't have any fresh water and you had a lot of permeability, salt water would intrude into the land forever. Okay? Of course, not forever, because you need a very high permeability to intrude forever. But the extension of saltwater intrusion may be very, very relevant. It may reach the land, it may intrude into the land for kilometers if the permeability is high and you don't have freshwater fluxes.
Sorry, how would you describe the freshwater in Iceland?
Sorry, freshwater?
In Iceland.
Because in an island you have, of course, it is collecting rain, and given that the land is elevated over the ocean level, because otherwise you wouldn't have an island, you have some fresh water flowing from the land to the sea. So when I said you always have some fresh water flowing in the underground toward the sea, there is permeability, the reason is that the land by definition is higher than the ocean. It's collecting rain, and therefore you have some fresh water flowing into it. And there is an equilibrium between the flow of fresh water and the intrusion of salt water. Fresh water is at a higher level with respect to salt water. Higher level because land is at a higher level, and in order to have a flow of water into the ocean, the fresh water has to be higher than the ocean. And of fresh water over the ocean means available energy to travel to the ocean. Available energy. The higher the freshwater level, the faster the flow of fresh water to the ocean. So if you have fresh water that is just a bit above with respect to salt water, it means that the energy of fresh water and the energy of salt water are comparable. And therefore, this means that salt water may prevail or has a comparable energy. If fresh water is much higher, then there is more energy by fresh water, in fresh water, that puts back salt water into the ocean. So the position of this interface, which is called their interface correctly, the position of the interface is driven by the height, lowercase h, of fresh water over the ocean. We will see this in detail. We will see the analytical procedure to determine the interface, the position of the interface, to locate the interface. For now, just keep in mind that it's important what is driving saltwater intrusion is, of course, sea level, and you cannot have any influence on that, and the level of fresh water above the sea level. Okay? And if you reduce the height of the fresh water, the level of the fresh water, for instance, because you take it, like you dig a well is, you know what is a well? It is, okay, perfect, to get water, and you reduce the level of fresh water, then automatically you cause a saltwater intrusion. And this is extremely delicate, because it's important to be aware in advance that we are impacting on that. Of course, if you have land subsidence or increase in sea level, you know, the equilibrium is compromised. And land subsidence is far more important, depending on the region, of course, than raise of sea level. So now we are much concerned about sea level rise today because of climate change. But actually, if we look at the amount of sea level rise from 1850 to today, we will have a lecture on that, it's 20 centimeters, 15, 20 centimeters. If you look at the subsidence in this region in the past 150 years, it's much more than that. So we have to be very concerned about subsidence because it's something that sometimes we neglect. It may be caused by human impact because if you extract oil and gases, you increase subsidence. And, you know, it is a driver of the saltwater interface. And the saltwater interface, if it gets into the land, it's a big problem because if the roots of the trees may get in touch with the salt water, so trees may die. And also if you have wells that go deep in the soil, at a certain point it already happened, you get salt water from them. So it's something to really keep into account. Now, as I said, you need to get an understanding of this. And then the understanding gives to you the basis for developing a theory to explain what's going on. Because, as you well know, you are engineers, as you well know, in order to support your design, you have to build a theory, you have to build a model that gives to you the design variables that support the design of the structure or the actions anyway. Now, the theory, in order to understand the evolution of beaches, is coastal hydrodynamics and morphodynamics. And this is what we focus on. So we have to understand what is hydrodynamics. Hydrodynamics is the dynamics of water close to the coastline. Dynamics of water implies dynamics of waves and the dynamics of fresh water. And then there is morphodynamics, which is the dynamics of the beach coast morphology. You have to understand the drivers of coast morphology. You have to understand how these drivers interact with the human impact and at the end determine the evolution of the coast. And it's not easy, but still we have the means, we have the data, and we have the theories that allow us to build proper models. And this is, as I said, our field. And you know, I mentioned that it's not easy. It's not easy because these are processes, when we talk about hydrodynamics and morphodynamics, these are processes that evolve according to different time and spatial scales. Different time scales, there is seasonality. Seasonality means that hydrodynamics and morphodynamics change with the season, of course. We all know that beaches are eroded mainly during winter. And the reason why they are eroded during winter is that during winter we have the sea storms that are more important. And usually much of the beach erosion occurs during sea storms. So there is a seasonal change. And this is taking place according to a seasonal time scale. But then it's an intra-annual time scale. But then there are other scales that are relevant at the interannual scale, which means that climate and therefore circulation of winds, circulation of sea waves, they are subjected to change also on a time scale of tens of years, according to cycles. And some of them are difficult to explain. Seasonality is easy to explain, but sometimes we observe changes that are reverted after 15 years, like direction of winds, direction of waves, and these are difficult to explain. And also there are changes of climate that occur over a time scale of millions of years, like glaciations. Again, they are difficult to explain. There are hypotheses about the nature, the origin of glaciations, but we are not sure about this. And then there is climate change. When we say climate change, usually we mean changes in climate that are induced by humans. Okay? When we say climate change, usually we imply that. And this is, you know, it's a very relevant issue, very popular issue, but again, this is very complex. We will have a lecture on climate change. It's not easy to predict how climate will evolve due to human activities. Because, you know, the main reason is that it's difficult to predict how climate naturally will evolve. Climate has always been changing for a kind of natural evolution. Change of orbits, change of composition of the atmosphere due to eruptions. So there is some natural variability which we don't understand, which is now superimposed to a human-induced variability. But again, the picture is not clear. So if we look at the television and the media, we know that there are models predicting some changes by 200 and 2100. Okay, 2100 means 8 years from now. There are changes predicted by models, but these are not certain. These are hypotheses. So it's again complicated, and we have to try to understand what's going on from a technical point of view, which is a completely different story. One thing is if you talk about hypothesis, and then we say, okay, the sea level may rise suddenly by 1 meter. But from a technical point of view, what does this imply? It means that if I design now a breakwater, should I take into account a possible sea level rise of 1 meter? Absolutely not. We have to translate in technical actions, technical terms, what is predicted by models that are not conceived for this. Keep in mind, climate models are not conceived for supporting engineering design. They are conceived for producing a what-if scenario, like it may happen this, but it's a completely different story. To build a model to support the technical design. And this is something that is often overlooked. And this is why when you look for technical details, how should an engineer design a structure in the presence of climate change, you don't find any indication, any technical indication, any technical guideline, because it's not clear, it's complex, and we have to elaborate our interpretation. We need it because administrations, people, they ask for it. I am involved in water resources management, and people tell me, what about climate change? So, okay, you give me water now, but what about in 50 years from now? And we have to give a reply. Okay, so we will focus on these issues, coastal hydrodynamics and morphodynamics. Not really hydrodynamics, because you already had some lectures with, not all of you, but most of you had lectures with Professor Archetti. She already explained to you how wave behave, how wave work. We will focus especially in morphodynamics. Okay. Now, let's try to get into play by taking into account some basic features, important features of beaches. First, beach is a gradual transition between the land and the sea. A cliff coast is not gradual, it's a clear transition. If you look over a map, there is a clear transition in the presence of a cliff coast between land and sea. The beach is a region where you have sometimes sea, sometimes it's dry, and by definition, we extend the beach from the low water mark to the highest high water mark. And so basically you get the highest high water mark and the low water mark, and we define beach all of this region. The dune is part of the beach, even if it is reached by water, maybe every 50 years, and this is why you have vegetation there. But it's still part of the beach. Okay, now, most of you, as I said, had lectures with Professor Archetti in ocean engineering. Okay. Now, as such, I go back to my page, just 1 second. As such, you already talked about mechanics of sea waves. And here, I think there should be the figure, but no, it's not here. Anyway, let me look at this figure. At the PowerPoint. You already know about mechanics of sea waves. I decided last year, in the second year I taught this course, not to talk about mechanics of sea waves anymore, because I thought that there was an overlap. But there is the problem that at least some of you didn't have any lecture with Professor Archetti. So, what I decided to do is to leave the webpage with the lecture in my website, and to leave it within the material, educational material that I give to you. But I decided not to lecture on this. And this is the approach that I would like to use this year as well. Now, but I need to give instruction to those of you who didn't have any lecture with Professor Archetti. So give me 5 minutes, but in these 5 minutes, I suggest to you that everyone pays attention, because I am clarifying what I may ask at the exam. Because even if I'm not teaching mechanics of sea waves, this is something that you necessarily need to know. And therefore, I at the exam I may ask something, and my questions will be very specific, very limited, my possible questions. So I suggest that all of you pay attention to this. So, about the mathematical description of sea waves. Sea waves are described by the Laplace equation, which is this one. It doesn't, sorry. This is the Laplace equation. Okay, where phi is the potential and x and z are the spatial coordinates. We assume that waves, we are talking about a plane wave. So the plane wave is depending on only two coordinates, which are z, the vertical coordinate, and x, which is the coordinate that is given by the wave direction of travel. Okay? And they depend on time. Okay, this is Laplace equation. I may ask you how Laplace equation is derived. So let me go back. It's very simple. First of all, we start from getting aware that when we describe a fluid in motion, when we describe hydrodynamics, so we want to describe the motion of a fluid, we need to describe the velocity vector, v. Depending on the relevant spatial coordinates, x and z, as I said, and the time coordinate. Okay? Now, this is valid again for plane waves. Plane waves are only varying along the vertical direction and the longitudinal direction, which is the direction of travel. We assume plane wave, which means no variation in the transversal direction, perpendicular to travel. Do you understand? The wave travels parallel to itself. Okay, parallel to itself. In the transversal direction, which is this direction, she moves in this direction. In the transversal direction, there is no change of any hydraulic parameter, and in particular the wave height doesn't change. This is the plane wave. Now, if you look at the sea, you don't see plane waves. You see a situation where, more or less, you see that the big changes are along the vertical and along the direction of travel. So they break, for instance, and they break along the direction of travel. Break means that at a certain point they fall, okay, and there is a lot of turbulence along the direction of travel. Usually, if you look at the transversal direction, when they start breaking, they break for the whole extension of the transversal direction. This means that the wave is close to plane. But if you want to be very strict, this doesn't happen. So when you see breaking, it's not true that breaking occurs at the same transversal longitudinal coordinate. There are changes in the transversal direction. Okay, so this is a first simplification, an assumption, which is needed because when you want to describe a very complex process, like movement of a fluid, which is a 3D one, usually, so velocity vector depends on the three spatial coordinates and time. This is very complicated. What you do usually, in order to simplify the problem and to make it tractable, is to neglect changes in one or two spatial directions. And therefore, you reduce from a 3D problem to a 2D or 1D problem. Is it clear to you what I'm saying? Okay, so plane waves, only 2D problem. Okay, so the velocity vector, which again I need to describe motion, sorry if I repeat, I want to make it clear. Describing motion of a fluid means describing the velocity vector for any relevant spatial coordinate, only two, and for any time. It's still very complicated. Keep in mind, spatial coordinates are real numbers. It means that for any fluid particle, you have to describe the velocity vector. Very complicated. We need to simplify it again. Okay? This description usually is extended to a contour volume. We define the contour volume, our volume of reference. And this contour volume may be fixed in space and time. So fixed volume, like this room. I want to describe the motion of waves in this room. It's fixed. Geometry of the contour volume fixed in time. And this means that we are adopting an Eulerian approach. Or the contour volume may move with the wave. I describe always the same water, not the same space, the same water. Lagrangian approach. We will focus on an Eulerian approach mainly. But in any case, keep in mind that we have a contour volume. This is the concept that I want you to get. So something we are interested in. We cannot describe the whole ocean, okay? We select a volume to describe. Okay, perfect. Now, we need to simplify the problem. We assume that water is incompressible. We can do that because we refer to an environment, the coast, where there is little depth of water. Water is actually compressible, is poorly compressible. You need